Hello everyone, I am Dr. Munish Kumar Bharadwaj from School of Engineering and Technology of IGNOU. So in last lecture, I discussed with you the IS code method of mix design. Here I will discuss with you an illustrative example on IS code method of mix design. So let us look at this example, and through this example we will come to understand that how we can design the mix with the help of IS code method. So here you see the data regarding this mix design. First of all, the design stipulations. Characteristic compressive strength required in the field at 28 days is 20 Newton per mm square for the mix to be designed. The nominal maximum size of aggregate is 20 mm. Shape of coarse aggregate is angular. Degree of workability required at site in terms of compaction factor, it is 0.9. Degree of quality control available at site as defined in table 2 in our last lecture. You saw table 2 giving that data related to the degree of quality control. So here, referring that table, here we want for this mix that degree of quality control available is good, and the type of exposure of the structure to which the structure will be subjected, according to that table 3 data, here it is mild, means the structure is to be exposed to the mild environment. The test data of the material which we have to determine from the laboratory actually. So we are taking here that specific gravity of the cement 3.15, that is to be tested basically. I am taking this data that it is done in the lab and we are using that. The specific gravity of fine aggregate is 2.60. The specific gravity of coarse aggregate is 2.60. The compressive strength of cement at 7 days satisfy the requirement of IS 26976. The water absorption in percentage by weight in case of coarse aggregate is 0.5%, and in case of fine aggregate it is nil. Then free surface moisture, in case of coarse aggregate it is nil, and in case of fine aggregate it is 2%. And the sieve analysis results gives this following data. Coarse aggregate, it is 2 types, type 1 and type 2, available at site as shown in column 2 and column 3 here. The sieve size 20 mm. The percentage passing for type 1 aggregate 100%, for type 2 100%. Standard grading as per IS 38370 is 10. Sieve size 10. The percentage passing is 0 for type 1 and 71.2 for type 2. And sieve size 4.75 mm. Percentage passing is 0. And percentage passing is 9.4 for type 2. For 2.36 mm sieve, the percentage passing for type 1 is 0 and percentage passing for type 2 coarse aggregate is 0. So that way this data is obtained from the sieve analysis. For fine aggregate, only one type of fine aggregate is available at site, and for sieve size 4.75 mm, percentage passing is 100. Then for sieve size 2.36 mm, percentage passing is 100. For sieve size 1.18 mm, percentage passing is 93, and for 600 micron sieve, percentage passing for this aggregate is 60, and for 300 micron of sieve it is 12. For 300 micron sieve it is 12%, and for 150 micron sieve it is 2%. So that way this is a sieve analysis for fine aggregate, and this fine aggregate conforms to the grading zone 3 of table 4 of IS code 38370. So this way we have just found out that what is the result of the sieve analysis for fine aggregate, and also to which grading zone it conforms to according to the IS code. So with this data, let us design the mix. So here coarse aggregate 1 and coarse aggregate 2 will first be blended to arrive at standard grading curve, and we shall use trial and error method for this. So what we see from this table, that for sieve size 20 mm, 10 mm, 4.75 mm, 2.36 mm, percentage passing for type 1 and type 2 are given here. Then we have done here two trials. In first trial, what we are doing basically, we are using 50-50%, means equal amount of type 1 and type 2. Then in second trial, what we are doing, we are taking type 1 aggregate, CA1 aggregate as 60% and coarse aggregate 2 as 40%. Then we see that after mixing in first case, when we are using equal amount for the two type of coarse aggregate, it is passing through 20 mm sieve as 100%. For second trial, in which we are taking 60% as type 1 and 40% as type 2, the percentage passing through 20 mm size sieve is 100%. In case of sieve size 10 mm, for first case, the percentage passing is 35.6, and for second trial it is 28.5. For sieve size 4.75, for first trial the percentage passing is 4.7, and for second case the percentage passing is 3.7. For sieve size 2.36, the percentage passing is 0 for first case as well as for second case also. So here, based on this result, what we will do, we will adopt the proportion 2, means the trial 2, in which the proportion is that type 1 is 60% and type 2 is 40%. This we will adopt. Now let's move for the design. So with this blending of the aggregates, we move to our step 1, means deciding the target mean strength. Hemsworth constant for 5% risk factor is 1.65, and standard deviation either can be determined by testing cube or through table 1. The table 1 which we discussed in our previous lecture of IS code method design of mix. So here also you can see this table. This is the table, and from this table you can get the standard deviation value. So in this case, the standard deviation is taken from table 1 against M20, and for good degree of control, and standard deviation for M20 and good degree of control is 4.6 in the table 1. So using these values and putting this equation, F target will be FCK plus K into sigma, FCK you know 20 Newton per mm square, K is 1.65, that is Hemsworth constant, and sigma standard deviation 4.6 from table 1. So this comes out to be 2.76 Newton per mm square. So here, after putting these values of FCK, K and sigma, we get F target as 27.6 Newton per mm square. Let's move to step 2. Step 2 is selection of water cement ratio. So water cement ratio against target mean strength of 27.6 Newton per mm square from figure 1 is 0.5. Just see the figure 1, and against the target strength of 27.6, you will get the water cement ratio as 0.5. If cement strength at 28 days were given, then we could use figure 2 for getting the water cement ratio. However, this water cement ratio is to be checked against durability requirement from table 3, as we discussed in our previous lecture. Here again you can see the table 3. Taking this case as reinforced concrete, the maximum water cement ratio against mild exposure as given in table 3 you can take as 0.65. Hence, lower of the value of 0.5 and 0.65 is to be adopted, and lower value is 0.5. So we will take the water cement ratio as 0.5. Now next step. Step 3 is determination of air content. The air content means the entrapped air is determined from table 4. You see the table 4 here, and this air content will be determined from this table against maximum size of aggregate of 20 mm, and this value in this table is 2%. So we will take this air content as 2%. Let's move to the next step, which is step 4, that is determination of water and cement content. As in this case, concrete grade is M20, which is less than M35. Table 5 is used to determine the water and sand content because it is used for medium strength. So here you see the table 5. Against 20 mm maximum size of aggregate, water content per cubic meter of concrete is 186 kg and sand content as percentage of total aggregate by absolute volume is 35. So we will be taking these values from this table. However, these values are for standard reference conditions mentioned earlier while explaining the mixed design steps. Hence, corrections are to be applied on these values for departure from standard reference conditions, and this is to be carried out in step 5. So step 5 is next is correction on water content and sand percentage. So the corrections are to be applied based on table 7, which is represented here in table 8. So let us see the table 7 and then the results will be reported in table 8. So you see the table 7, and based on this table 7 we are preparing this table 8 where we are reporting the corrections. As you see from this table, in first column parameters are given, in second column values as per standard reference conditions are given, then in third column values as per present problem, the given problem are given. Then we see the departure, what is the departure from the standard reference conditions, in case of this problem. And then next column you see the correction in water content, and in next column you see the correction in sand in percentage. So for sand zone 2 and sand zone 3, because as per reference condition sand zone 2 is used, and as per the problem, given problem, sand zone 3 is used. So water cement ratio, here you see in standard reference condition it is 0.6, whereas for our problem it is 0.5. So departure is negative 0.1. So the correction in water content is 0 and correction in sand percentage is -2. Compaction factor in standard reference condition is 0.8, whereas for our condition it is 0.9. So departure is plus 0.1. The correction in water content, here it is +3 and in sand it is 0. Shape of aggregate, the angular shape of aggregate is used in our problem, as well as it is taken in case of standard reference conditions also. So that way we see that total correction in water content comes out to be +3 and total correction in sand percentage comes out to be -0.35. So that way it gives you the summary of corrections needed here. So based on the results of these corrections, we will correct the sand content and the water content. So the corrected sand content as percentage of total aggregate by absolute volume will be 35 minus 3.5. So that will be 31.5%. If you want to represent in fraction, then you have to divide it by 100. So that fraction, that is P, will be equal to 31.5 upon 100, that is 0.315 in fraction, otherwise 31.5%. And also the corrected water content will be 3% of correction was there, positive means plus correction. So here the water content will be then 1 plus 3%, means 1 plus 3 upon 100 means 1, total will be 1.03, and you will multiply by this factor and then we'll get the corrected water content, which is 186 into 1.03, it is 191.6 kg per meter cube. If you want to represent in volume, then 1 kg equal to 1 liter, so again it will be 191.6 liter per meter cube. Then we move to next step, that is step 6, calculation of cement content. Now up to this point, what we have decided, that water cement ratio is 0.5, water content is 191.6 kg per meter cube. So the cement will be 191.6, because from the water cement ratio, which is water upon cement, which is equal to 0.5. So from here you can calculate the cement as water content divided by water cement ratio. So that way 191.6 upon 0.5, you will get 383 kg per meter cube. Means for 1 meter cubic of concrete, you need 383 kg of cement. So this value is to be checked for durability requirement from table 3. So look at this table 3, and from this you will check the amount of cement for durability. So in the present example, against mild exposure and for the case of reinforced cement concrete, the minimum cement content is 250 kg per meter cube, which is less than 383 kg per meter cube. So hence this value is correct. So we will take up the cement content as 383 kg per meter cube. Now next step, step 7, is determination of fine aggregate and the coarse aggregate content. So put the relevant values in equation for fine aggregate that we studied in that last lecture, which was volume of entrapped air in fraction equal to W plus WCE upon SC plus 1 upon P Wf upon Sf into 1 upon 1000. Here put the values in this equation and you will get the weight of the fine aggregates as 546 kg per meter cube. Similarly, from the equation of coarse aggregate, you can calculate the weight of the coarse aggregate as 1188 kg per meter cube. So as coarse aggregate type 1 and type 2 are in the proportion of 60 and 40, weight of coarse aggregate 1 per meter cube of concrete will be weight of coarse aggregate into 60% means 0.6, means 1188 into 0.6, which is 712.8 kg, and weight of coarse aggregate type 2 for per meter cube of concrete will be 1188 into 0.4, which is 475.2 kg. So that way two type of aggregate, coarse aggregate values we have calculated. So finally, from these calculations we get the required mixed proportion, which is as follows: that water content is 191.6 kg, cement is 383 kg, fine aggregate 546 kg, coarse aggregate type 1 712.8 kg, coarse aggregate type 2 475.2 kg. Now step 8, which is correction due to absorbing or moist aggregate. The fine aggregate, which is having the 2% of surface moisture, which it will contribute towards mixing water. Hence, that much of water has to be reduced from the mixing water. After contributing this surface moisture, means after it attains the surface saturated dry condition, SSD condition, its weight decreases. Hence, so much weight is to be added with the weight of fine aggregate. So, weight of free surface moisture, as you know, 2% is there. So, 2% of 546 means 0.02 into 546, that is 10.92 kg. This is the weight of the free moisture. Then correction to be applied to the water content, because this additional water will add to the water to be added in the concrete. This has to be reduced then, because it is coming from the fine aggregate. So then correction to be applied to the water content to be added is minus 10.92 kg, and correction to be applied to the weight of the fine aggregate will be plus 10.92 kg, means we have to add 10.92 kg of fine aggregate more. Coarse aggregate at site is absorbing type and its water absorption found to be 0.5%. So therefore correction to be applied to water content, and here 0.5% means 0.5 upon 100, 0.005 into 1188 kg. This is 5.94 kg. And because this coarse aggregate is absorbing water from the water meant for mixing to the concrete, so here this correction will be positive type, means we have to add more water due to this absorbing type of the coarse aggregate, and this is 5.94 kg. So correction to be applied to coarse aggregate 1, because 60% is there, it's 5.94 into 0.6, that is 3.564 kg, that is minus 1, because we have to reduce that aggregate, and correction applied to coarse aggregate type 2 will be 5.94 into 0.4, because 40% was there, so it is 2.38 kg. So these are the correction for the coarse aggregate and water to be applied to the concrete. So finally here the corrected mix proportion is that water which was we calculated earlier taken as 191.6 Due to fine aggregate, the correction is minus 10.92 kg, and due to coarse aggregate, correction is plus 5.94 kg. So the corrected water content is 186.62 kg. Cement 383, no change. Fine aggregate we calculated as 546, but correction due to fine aggregate free moisture is 10.92 kg, and finally it is 556.92. For coarse aggregate type 1, the calculated value was 712.8 kg, but correction due to absorbing type of the coarse aggregate, it is minus 3.564 kg, so final value is 709.24 kg. And for type 2 coarse aggregate, calculated value was 475.2 kg, but correction due to coarse absorbing type of coarse aggregate is minus 2.38 kg, so here it is 472.82 kg. So these are the corrected mix proportion. Now the final step is the trial mix. So let us do the trial mix number 1. The mix proportion as calculated in step 7 forms the trial mix 1. The local correction for moisture condition of aggregate is to be applied on this proportion as shown in step 8. Then with this corrected proportions, concrete is manufactured and tested for fresh concrete properties requirements, that is workability, bleeding, finishing and other qualities. In this case, it was found to have workability of 0.8 in terms of compacting factor against requirement of 0.9 with no bleeding. The visual observation of the mix was found to be undersanded. So let us go for trial mix 2. To increase the workability from 0.8 compaction factor to 0.9 compaction factor, as increase in water content by plus 3% is to be made as per table 7. The corrected water content will be 191.6 into 1.03 means 197.3 kg. As the mix was found to be undersanded, an increase of 1.5% is made in sand content. It is from experience basically. The corrected sand content is taken 31.5 as found in step 5 plus 1.5 means here it comes out to be 33%. As mentioned earlier, to adjust fresh concrete properties, the water cement ratio will not be changed. Hence, water content is now 197.3 upon 0.5. It is 0.5 means water cement ratio. So it comes out to be 394.6 kg, which also satisfies the durability requirement. So now applying the equation for fine aggregate, you can calculate again the weight of fine aggregate and putting all values there, you will get the weight of fine aggregate as 564 kg. Similarly, from the equation for coarse aggregate, you can calculate the weight of coarse aggregate, which comes out to be WC equal to 1145 kg. Herein type 1, 60% of it will be taken, which comes out to be 687 kg, and for type 2, which is the 40% of the coarse aggregate, total coarse aggregate, so it is 40% of 1145 means 458 kg. So trial mix 2 will have the proportion as water as 197.3 kg, cement as 394.6 kg, fine aggregate 564 kg, coarse aggregate of type 1 687 kg and coarse aggregate of type 2 as 458 kg. So these are the proportions for trial mix 2. A local correction due to moisture condition of aggregate is now to be applied on this proportion as mentioned in step 8. With the corrected proportion, concrete is cast and tested for fresh concrete properties, that is workability and visual appearance, which were found to be 0.91 compaction factor and cohesive respectively. So it is based on the results basically. This compaction factor is based on the test results. Once the fresh concrete properties are adjusted, 3 cubes are cast with the same mix, means trial mix 2, and tested for 28 days compressive strength. Then we will go for the trial mix 3. In case of trial mix 3, water cement ratio is varied by plus 10%, keeping water content constant. In the present example, water cement ratio is raised to 0.55 from 0.5 because 10% increase we are doing. The increase in water cement ratio of 0.05 entails a correction in sand content as per table 7. We have to do the sand correction in the sand content. So correction in sand content will be plus 1%. Hence corrected sand content will be now, earlier it was 33 sand content percent, so 1% more, 33 plus 1, 34% will be the sand content. And in fraction, if you do 34 divided by 100, so P will be 0.34. The cement content will be equal to keeping the water content constant. So that water content divided by the new water cement ratio, you can calculate the cement content. So water content is 197.3 divided by new water cement ratio, that is 0.55. So that way we get the cement content as 358.7 kg. So now we can calculate the fine aggregate, weight of fine aggregate and weight of coarse aggregate as we did earlier by applying the equations for fine aggregate. So finally, the summary of all these trial mixes are given in this table that you see here, and in this table in first column trial mix number is given, then the quantities of materials per meter cube of the concrete in kg are given for cement, water, fine aggregate that is sand, then coarse aggregate of type 1 and coarse aggregate of type 2. Then concrete characteristics are also mentioned here, and finally in the last column you get the remarks. So for example, I read you for trial mix 1, the cement is 383 kg with water cement ratio of 0.5. Quantity of water is 191.6 kg. Then quantity of fine aggregate, that is sand, is 546 kg, which is basically 31.5% of the absolute volume. Then quantity of coarse aggregate of type 1 is 712 kg and coarse aggregate type 2 is 475 kg. Workability in terms of compaction factor that was achieved was 0.8, and by visual observation you find that the mix is under sanded. So that way, similarly for different trial mixes, trial mix 2, 3, 4, these properties or the proportions are given here, amount of different ingredients are given here. So this way you can design the concrete mix as per the IS code method. I hope you must have understood it nicely, and you will go through the e-content also, so that way you can understand it in a better way. So thank you for watching.